Welcome back to another video. So the first practical sequential circuit that we'll be designing is what's called a decade counter. And it is a circuit that counts from decimal 0 to decimal 10 and then resets back to decimal 0. Right? It actually counts the number of clocks. So if I show in terms of timing diagram, you will have some clocks. This is my clock signal. Fine, so this is my clock. Again, it will respond to the positive rising edges. And so this is the circuit wherein the states let's drop some projections. The states will actually keep a track of the number of clocks that have passed. Fine, so if I start from here, it will be 0. Then as first clock comes, count 1. Then second clock comes, the count will change to 2. Third clock comes, count will change to 3, so on. And once it has reached 10, then on the next positive edge of the clock, it will reset back to 0 and again start counting. So this is its behavior, right? And we'll try to design it using the methodology that we worked out the last time. Right? So this pehla step here, we have to capture the finite state machine. So this is the first step. Based on this behavior, we have to capture the finite state machine of a decade counter, right? So I will just remove this. Now, as far as okay, it's not dropping. Anyways, yeah, let's just keep it. So this is the first step. Now, as you can see, there are how many 11 states. You start from 0, then from 0 you move to 1, then to 2, 3, 4, 5, 6, so on up to 10. So if I draw the finite state machine, it will have 11 states, starting with state 0, state 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Fine. So this state, let's call it 0. This one based on, how much it has counted in that particular state. 5, 6, 7, 8, 9, 10. Please remember, a finite state machine, it has a finite set of states. So in this case, we have an 11 state. Then we have to specify an initial state. So let 0 be our initial state. Then another thing is we have to show the transitions. So the transitions are shown like this. So it is implied that every time a positive clock edge comes, my circuit will be moving from one state to the next state. Fine. There are no external inputs, there are no external outputs. Fine. So this is the finite state machine of a simple decade counter. It has 11 states, and every state is named on the basis of the count that it holds. Fine. Again, remember, state is nothing but the behavior of a circuit in a certain clock period. Right. So if state 0, it is the behavior of the circuit when there is no clock. State 1, behavior of the circuit when one clock has passed. state 2 behavior of the circuit when 2 clocks have passed. So this is the first step. We captured the FSM. The second step is we have to create a standard architecture. And at this step, we have to specify what is the width of my state register. Now there are 11 states. And in binary to code 11 states, you will at least need 4 bits. So this means my standard architecture will be something like this. It will have a combinational path, combinational part, combinational logic that we will later resolve. This will be the combinational logic. And it will have the memory which we have specified that it is going to be a 4-bit state register. Show it something like this. Fine. So this is the combinational logic that I will resolve later in the coming steps. And as of now, I have resolved that this is going to be a 4-bit state register. Obviously, it will have a clock. There are no external inputs, there are no external outputs. Fine. So the only inputs and outputs that we have are the state inputs. I can show them here. These are the only inputs. And these are basically the outputs that have been stored from the circuit previously. So they are something like this. Third one, and then the fourth one. Something like this. And we'll have to name them. So we'll call these as a convention which follows. So S3, S2, S1, S0. So these actually represent the current state of the circuit. And then you can name them next to N3, N2, N1, specifying what will be the next state of the circuit. So this is the second step. We have created a standard architecture in which we have actually resolved this part. Okay, what is the width of my state register? And the third step is that we have to encode the states, because for implementation, we need the states in binary. So third step is encode the states. And the straightforward scheme that we can use to encode the states is based on assigning a binary code as per the decimal value. Fine. So if I have state 0, then state 1, state 2, 3, 4, 5, and then let's say 6, 7, 8, 9, 10. Right? So the first state I'll be assigning 0, 0, 0, 0. That is the 4-bit equivalent of decimal 0. Then second state 0, 0, 0, 1, and so on. This is the straightforward scheme, analogical scheming coding that we can use here. Then 5. Likewise, we have 6, 7, 8, 9, finally 10. This will be my initial state, then these will be my transitions. So in this case, it is pretty straightforward in the sense we don't have external inputs that control the transition. So these transitions that I'm showing right now, it is implied that they happen every time a positive edge of the clock comes. Fine. So this will be my fourth step where I have encoded the states. Then third step rather. The fourth step will be from this we have to create the state table. And as I mentioned in the previous video, a state table will list inputs on one side and outputs on the other side. Fine. So we'll have inputs on one side and the outputs on the other side. And generally speaking, you can have two categories of inputs, state inputs and external inputs. Similarly, you can have two categories of outputs, state outputs where you specify the next state and the external outputs. But in this circuit, we don't have external inputs and external outputs. So on the input side, I will have the current state, which is this S3, S2, S1, S0. And on the output side, I will have the next state, N3, N2, N1, N0. And based on this, we'll create a state table. Fine. So starting with the or the initial state where it is 0, 0, 0, 0. Then from this, my next state is going to be 0, 0, 0, 1. Then 0, 0, 0, 1. Then my next state is going to be 0, 0, 1, 0 based on this finite state machine which is encoded. Likewise, I can complete the table. Let me just quickly complete it. Fine. Let's see if we got it right. So this will be fine. 4 will be 5, 5 1 to 6, 6, 7. Maybe we'll have to add one more because it resets back to 0. So when it is 1, 0, 1, 0, then my next state is going to be the original state. Something like this. Okay, so this is the state table, the fourth step. And based on this state table, we have to actually what you call resolve the combinational logic. So you will get equation for n3, n2, n1, and n0, four separate Boolean equations, and then we have to solve them. So we have actually already solved it. So these are my original equations in min terms. Important thing here is you can use the don't care conditions, because with four Boolean variables, you can have 16 explicit conditions. Out of those 16, only 11 have been resolved here. So 5 you can treat as don't care when you try to simplify. So this is what I've done here. I have pre-done it because this is something we have done many times. So I thought just to save some time. So these are the original equations, n3, n2, n1, n0 as sum of min terms with the don't care conditions. Then I have used the four variable k maps to resolve them, and ultimately I have arrived to these simplified equations. And this is basically that will implement my combinational logic. So these are the simplified equations after solving using Boolean. So I will have to draw it here. So I'll do one thing. So this would basically implement my combinational logic. So let's have the state register. I'll try to draw it here, the overall circuit. So I will have my state register here. This is a 4-bit. Okay. So this much we had already specified in the second step when we created the standard architecture. So this is 4-bit state register. Fine. This is its clock. And from here, I have 4 state inputs. Let this be S3, S2, yeah, we'll do one thing just to keep track of. We'll use different colors. Then let this be for S1 and let this be for S0. Fine. So this is for S3, S2, S1, S0. Fine. Then for N3, I need S3, S1 complement. So S3 means an input from here and a complemented input from S1. And I will combine them using an AND gate. Fine. Then I need S2, S1, S0. So this is S2, S1, S0. Again, combine them using an AND gate. Then these two I will combine using an OR gate. And that will be my N3. Fine. And that N3 you can actually feed like this to the state register. Fine. Similarly, then you can implement N2. For N2, I first need S2, S1 complement. So S2 is here. S1 complement. So S1, I will put a NOR gate. Then combine them using a small AND gate like this. Fine. Then I need S2, S0 complement. So S2 is still here. S0 complement. Combining them using an AND gate. Then there's a third term, S2 complement. So complement from here. Then S1, then S0. Again, combine them using a single 3-input AND gate. Then I will combine all 3 of them using a 3-input OR gate, something like this. And this will give me my N2. So let's complete the path here for N2. N2 will go this way, then like this. Fine. So this was N2. Next I have N1. And for N1 I need S1 complement S0. So S1 complement will be here. S0 from here. Combine them using an AND gate. Then I have S3 complement. Okay, that will come from here. S1, this one, then S0 complement. So something like this. Then combine them using an AND gate. Combine these two using a 2-input OR gate. So this will be my N1. Again, I will complete its path. Okay. Anyways, that's what this is. So this is for N1. And finally, I have N0. Let's complete N0. For N0, I need S3 complement. S3 complement is here. Then I need S0 complement. Here I have it. Combine them using an AND gate. Then I need S1 complement and S0 complement. Combine these two using an OR gate. Then again completing the path like this. Fine. So this is my N0, and this is the overall sequential circuit. Fine. So we have resolved the combinational path from the state table by going through this process, and this is a circuit for a decade counter. Fine. So we have used the methodology here. We captured the finite state machine, this one. Then we created the standard architecture wherein we resolved the sequence, the memory part. It requires a 4-bit state register. And you know that this is a state register. Since it is 4-bit, it actually means it will have 4 flip-flops. D flip-flop, J की flip जो भी है. So it is basically that thing. मैंने आपसे कहा था कि design of memory is if you are able to store this 1 bit, you just have to replicate the same thing. So flip-flop stores 1 bit. So if you need a 4-bit state register, you will use 4 such flip-flops. Fine, then we have encoded the states. In this case, the straightforward scheme is that for every decimal, you put a binary code, 4-bit binary code. From there on, we get the state table. We create the state table where in one side we have inputs and the other side we have outputs. So in this particular case, we had only state inputs and state outputs. From the state table, we got the state equations. We solved them, simplified them using K-map. And the simplified equations we implemented that resolved our combinational logic, and this is the final circuit. Fine. So in the coming videos, we'll design some more sequential circuits.